Think about what happens if a drop of red dye is added to a beaker of water. The color spreads as the dye molecules move randomly away from each other. In other words, there is a net movement of molecules from the area of high dye concentration, where the dye entered the water, to the area of low dye concentration, the water surrounding the dye. This process is called diffusion. With time, the dye becomes evenly distributed in the beaker. The water in the beaker is a single shade of pink, and diffusion no longer occurs. There is no net movement of dye from one area into another. Here's another beaker of water. A membrane is added to this one, dividing the beaker into compartments. The membrane is semi-permeable. This means only certain substances can pass through it. Water molecules move easily through the membrane. Suppose a solute, such as salt, is added to the water in both compartments, but not in equal quantities. More solute is added to the left side than to the right. The solute cannot pass through the membrane to even out the concentration, but water can. As a result, water diffuses from the area of lower solute concentration, the right compartment, into the area of higher solute concentration, the left compartment, until the concentration of solute evens out. This diffusion of water through a semi-permeable membrane is called osmosis. Every living cell is surrounded by semi-permeable membrane. Inside that membrane is the cytoplasm. The cytoplasm consists mostly of water containing many dissolved solute molecules. Recall that water can flow freely across a semi-permeable membrane. Recall also that the movement of water across a semi-permeable membrane depends upon the concentration of solutes on either side of the membrane. Therefore, whether water moves into or out of a cell will depend on the relative concentration of solute inside versus outside the cell. Suppose a cell is placed in a hypertonic solution. This is a solution in which the concentration of solutes is greater than the solute concentration in the cell. Water diffuses out across the cell membrane and the cell shrivels up. Now think about a cell placed in a hypotonic solution. The concentration of solutes in a hypotonic solution is lower than the concentration of solutes in the cell. Again, the flow of water acts to even out the solute concentration on either side of the cell membrane. Water diffuses into the cell, causing it to swell. More and more water flows in until eventually the cell bursts. Finally, consider a cell placed in an isotonic solution. This is a solution with the same concentration of solutes as the cytoplasm. Although water flows in and out of the cell, there is no net flow in either direction. The cell neither shrinks nor swells.